welcome everyone to this unplanned, unannounced episode of Iron Beetle. The story here is that today there are two of us. There is me, Matt and there is Chitanya. Chitanya, please wave for audience so that they don't confuse me with you. So Chitanya is a new member of our Target Battle team. Well, like he actually joined us last year as an intern, but right now he's full time. And this morning I was going to discuss a particular liveness bug. Well, not even liveness bug, a particular availability bug in Tagbital, which is waiting to get fixed. But we figured that, hey, let's do this live. Let's record this so that this is actually useful for someone else. Okay, so the plan is that, first of all, I want to explain how our checkpointing and write-ahead log interact with each other, like how durability of a particular transaction evolves over time. And then we'll discuss the actual bug, which is actually exceptionally great bug because there is like one very specific comment in the source code which is just wrong, which makes this like, very crisp logical bug. And then we'll discuss potential fixes. Okay, so please, Chitanya, like interrupt me with questions because that is your role right now to, two
Got it.
roles. First of all, to ask questions, and then second, if I start to tell something which doesn't make sense, which is like complete nonsense, then please tell me that as well. Okay, so the bug. The bug involves our write-ahead log and checkpoint. And for that, we need to understand the bigger structure behind our write-ahead log. We need to understand the checkpoint interval and that dreaded LSM batch multiple constant, which I'm complaining throughout this series. Okay, so let's start with the log. The goal of consensus, the primary purpose, is to take an unordered set of prepares submitted by the clients and arrange them in the single logical externally observable order to basically assign sequence numbers to each incoming prepare. You see that as time goes from left to right, we are going to have this log of ordered prepares, and my mouse is lagging horribly due to this double streaming, so bear with me. Okay, the problem with this picture is that, in Tagabitl, we want to make sure that everything has a fixed limit, so that we know that if we allocated enough resources to the startup, we never are going to run out of resources. And if you just, picture this log, it's going to be like infinitely long. And this just doesn't work. Like, you cannot store it amount of data. So periodically, what we are going to do is that we are going to take a bunch of prepares. I think I want this transparent. Okay, let's say we take 4 prepares and say, okay, so this is now a checkpoint. So at this point, you don't have to store all those 4 prepares in memory. You can discard them from your write-ahead log, and instead you only store the resulting LSM tree on disk. So this is the first approximation of our logical write-ahead log, is that it is a sequence of prepares which is subdivided into a sequence of checkpoints, where each checkpoint is checkpoint interval long. And here I think I need to actually go and show this. So we have now constants checkpoint interval. Yeah, these are checkpoint interval. So this is measured in prepares, and like every checkpoint interval prepares, we go and make checkpoints. Now, the reality is more complicated because we have this LSM batch multiple, which from this point on, I'm going to refer as compaction interval, because that's a better name which came up out recently and which we yet still have to use. So, what is this compaction interval? Another big idea behind Target is that it does batching. So rather than doing each individual piece of work one at a time, Target tries to batch many similar or identical pieces of work together and then process the whole bunch at the same time. This means that, in particular, when we talk about compaction and prepares, this means that if Target receives a bunch of prepares, they are not immediately, so like, you execute a prepare, you apply a state transition function to your internal state. Your internal state is now different after each particular prepare. And eventually, you want this internal state to be saved to disk as an LSM tree. But we don't do this transfer from in-memory to disk after every prepare. We batch using compaction interval prepares. So let's say that compaction interval is 4. That means that after we process these 4 prepares, we have 2 data structures. We have LSM on disk, and we also have kind of like superimposed on that LSM on disk. Let's draw this superimposed. And okay, let's make this red. And we have in memory table. And I'm going to make this much larger because it is impossible to read. Not this large. Okay, like in memory table, we have LSM on disk. So, if new request comes in, to figure out what is the state of actual state machine, we merge our in-memory data with our release data, and that's our view. And like this in-memory table is slowly accumulated whenever we append a new prepare. And once we append compaction interval of prepares, we actually go and start moving that in-memory table to disk in the process of compaction. And that means that these 4 prepares get to disk by the time by the time we append the next compaction interval batch of prepares. So let's make our picture slightly more closer to life. So we have this arrow of time.
One question there, Alex. And it's been a while since I've gone through the compaction code. But do we still have 2 versions of the in-memory of the data in memory? Do we still have like the mutable table and the immutable table?
Good question. So we actually did refactor this thing a while ago, and I think right now it looks differently to what you were seeing last summer during your internship. So we have this cache map, and I think right now, yes, table mutable and table immutable are essentially the same data structure. They are just like flipped. But the big picture is the same. So we have like some on disk stuff, we have some in memory stuff, and in memory stuff goes to on disk stuff. Every compaction interval prepares. So okay,
Got it.
so we have something, a picture which looks roughly like this. We have this black arrow of time, then we have these green checkpoints, and then we have blue compaction intervals. And the tricky thing is that do we have, yeah, is that this checkpoint hits disk when we process this next batch of prepares. So this is why we have like an off by one difference between checkpoint and the operation we currently are at. And that is handled by two functions in replica. There is, okay, let me zoom in quite a bit. There is op checkpoint, which tells you what is the latest op which is on disk, which is checkpointed. And then we have checkpoint trigger, which is the op where you should do the process of transitioning the previous batch of prepares to disk, or rather, so when you hit the checkpoint trigger, you know that the previous batch is already on disk, so you could actually do and update the superblock to point to the next checkpoint. Okay. But
And another question there, Alexei.
yeah.
So when we prepare a batch of writes, let's say, and I think we discussed that like a batch of writes which is equal to the compaction interval also indicates that now our in-memory table is full.
Yes.
And ready for flushing to the first level of the LSM tree. Why don't we start that flushing immediately, and why do we wait for the next batch to complete before we start flushing that in?
I think you actually do flush. So okay. When you okay, so checkpoint trigger is on the boundary between two batches. So so this is checkpoint trigger. When you are here, you know that this whole blue bar is in memory table, and you start writing it to disk. So at this point, you like move this to disk, and it hits the disk fully once you get to this point. Conversely, if you are here, you know that this stuff, so this batch, hit the disk. So you know, so at this point, you know that the LSM data for the previous checkpoint, so this whole thing is on disk. And now to complete checkpoint, you only need to update the root pointer. So again, this is big idea that everything is immutable. And like actual process of checkpointing means that you need to update just the root pointer. So at this point in time, you know the value of this root pointer, but this root pointer itself isn't stored on disk. On disk stores the old root pointer. So here you realize, okay, so I now need to checkpoint. And the checkpoint isn't actually the process of like, doing the checkpointing work. The actual checkpointing work is done by this point. So what checkpoint actually does is that it just writes the new superblock, which points to the new state on disk. Okay.
Got it.
So, and this is like already like pretty complicated with like this off by compaction interval checkpointed, but that's not all, because besides the so before we go next, let me kind of like try to explain one thing. So checkpoint is the current checkpoint. So this is the thing on disk. then op checkpoint next is the next checkpoint. So this is when the next time, like, well, kind of like when we checkpoint the next time, which is going to be compaction interval ahead of checkpoint next, then the checkpoint which will end up on disk is this checkpoint next. And this op checkpoint next trigger is the trigger for the next checkpoint. Because, well, we kind of like, we don't need to know the trigger for the current checkpoint because, well, if this checkpoint exists, that means that we are actually past the trigger already. There is actually, like, you know, a subtle thing here because when you start from disk after a crash, you start from a checkpoint. And there is a difference between how you process prepares when you process them normally before the crash and when you start up after the crash. Because when you start after the crash, you know that during the first compaction interval of prepares, you shouldn't actually be running compaction because, like, you know, this compaction is already on disk. So in terms of like our pretty picture, let's say we got somewhere to like this point, and then we like died here. So it's like big kaboom here. We start from this checkpoint. And when we process this batch of transactions, we actually don't run compaction code for this batch because, well, we know that, hey, it already is on disk, so we don't need to redo it. In contrast, when we normally process this in quote quote next checkpoint, we run compaction because at that point, at that point, our checkpoint points like to like here to the previous one. Okay, so that's why we have like op checkpoint next, trigger. Then we have op prepare max, which is relatively recent addition. So before op prepare max, the logic was that when a replica reaches checkpoint, it like sort of halts and waits until checkpoint is done before preparing any new prepares on top of it. Which means that the checkpoint is a latency spike in our latency graph. Again, it is not a huge spike because checkpoint doesn't do the checkpointing work. The checkpointing work have been done by the point of the checkpoint. So checkpoint just updates the root pointers, but still, it is an atomic update of the superblock, so it is for these writes, which are serialized through desync, so it's some amount of latency. So the idea here, to mask this latency, we allow the replica to, okay, can I close this window?
Also, Alexei, it seems like there's some issue with the stream as per Jiren, I think, who's watching it right now.
So you mean that the stream isn't, okay, actually, let me check.
Apparently there are some intermittent issues, apparently.
Actually, okay. Well, it seems okay right now. It probably crashed, and I'm not going to watch the stream right now. So sorry, like I will do I only will be answering Chitania's questions, simply because like I already have like 2 video streams and they make my computer crawl. So I'd rather not not get a stream. But thanks for a heads up. Anyway, if this stream crashes, as usual, this is all recorded and this is going to be on YouTube. Okay. So let's say that we are at this point, so right at the checkpoint trigger. Before, like in the old logic, we actually were standing here until the checkpoint was done before processing to this next prepare. In the new logic, the replica is allowed to prepare this whole next compaction interval of prepares. So actually, it is allowed to prepare pipeline worth of prepares. So preparing means that prepares are appended to the write-ahead log, and prepare case sent to the primary, and the primary considers those prepares as logically committed, but they are not executed until the checkpoint is done. So we kind of like mask latency because we allow the replication and consensus work. Allow replication consensus to work normally, and the actual execution is going to proceed once the checkpoint is done. Okay, so this is what this op prepare max is doing. So we have actually let's take a quick look at the implementation of these functions. So op checkpoint is what is the state on disk. So we get it from the current disk state, which is stored in the superblock. Checkpoint next is relatively simple. We look at the current checkpoint, and then we add checkpoint interval to this thing. So that is straightforward. Op prepare max is slightly confusing because we compute it for the next checkpoint. So it is not so kind of like the way I like to think about op prepare max is what op I'm allowed to prepare for the current checkpoint. But in the implementation, we actually say, okay, what is like the op for the next checkpoint? So that's why we like pass here op checkpoint next, and internally this basically just adds this pipeline prepare queue max. Okay, so that is basically the story. You append the prepares. At some point, you pass the checkpoint, but at that point, actually nothing happens. One compaction interval later, you pass the checkpoint trigger. At this point, you start writing the new route of the tree to disk, a new superblock, but you can continue actually accepting prepares. And you accept prepares up to op prepare max, which is a pipeline ahead of that. So in terms of actual our picture, we are going, I'm running out of colors here. We are going to have okay, I'm running out of colors, and so like this like pipeline, which in general is not really correlated with LSM batch multiple, because again, while we are preparing stuff, we are not actually applying any changes to the LSM. We just append them to write ahead log. So the question is, why do we even need this op prepare max? Can we like prepare like, I don't know, 1,000 prepares in the future, like million prepares in the future? What do we need? And this is where we go from logical picture to physical picture, because physically, like logically, our like timeline of prepares is infinite. Physically, we have pretty bounded write ahead log. Pretty bounded journal. Okay. In terms of source code, this bound between those two is exemplified by constant journal slot count. So okay, we are going to have like only this many slots in our physical journal on disk, and our physical journal is going to be a ring buffer. So that is kind of like the answer to why we cannot prepare just infinite amount of prepares. And the answer is that, okay, so let's say you are allowed to prepare somewhere like very far in the future, but that means because your journal is a ring buffer, you're going to overwrite some older prepare, which is obviously not correct. So right now, our task is to figure out like just how much prepares are we allowed to are we allowed to prepare? And well, kind of like this is exactly the point which we figured out wrong in Tagabit. So okay, let's kind of like start with a simple intuition. So okay, this is our journal. Like obviously, it should be long enough to hold an entire checkpoint. So we kind of like this is a checkpoint, and like obviously journal has to hold a checkpoint. And obviously it needs to be able to hold a compaction interval of prepares on top of that, so that we could actually trigger this checkpoint. And then it needs to hold this pipeline of prepares more, because we want to be preparing while we are committing. And this is sort of naive lower bound on the length of the journal. So it would be correct if the journal actually would, if the journal actually had more slots than that. But this is how many slots it has. Like this is like the minimum amount of slots you had to give it to not lose data irrecoverably, such that you cannot even like recover after a crash. Now, there is this very tricky question of when you are allowed to okay, scratch that. So let's rephrase like this whole question about which data should we store in our journal in a different way. Specifically, okay, at some point you add a new prepare to your journal and you are overriding an old prepare. And the question is, when you are allowed to override the old prepare? There is naive answer here. And naive answer is that you are allowed to override any data which you have checkpointed.
On disk.
So, okay, if you like get a prepare, you see, okay, so the prepare which would be evicted due to the ring buffer nature of the log is already past the checkpoint point, so I'm allowed to evict it. That seems reasonable, but this is actually buggy. So the question for you, Chitanya, can you understand why this is buggy? And like, it's okay if you don't answer it, because well, we also didn't understand the answer to this question until Whopper provided us with a seed which tells us why this naive solution doesn't work.
Okay. So the question here is again want to understand it clearly. So we want to figure out what part of the write ahead log we can safely overwrite with new ops while overwriting some old ops that are already in the write ahead log.
Yes.
Okay, so if we consider this particular scenario where we've checkpointed, like it seems like it more than 50% of the log, the log already. We want to find out what is the maximum after wrapping around. What is the maximum where we can write to, or something? Is that the question?
Even more specific. So, like,
Okay.
the naive answer you have is that you can overwrite everything which is already checkpointed by your replica.
Okay.
And kind of like that's the wrong answer. So I want us to
Okay.
find out why this answer is wrong. And it has to do with
Okay.
storage faults. So if you don't model storage faults, if you assume that the storage is perfect, then actually that's the correct answer. You
Okay.
like have to have op either in your write ahead log or in your checkpoint. But if you consider storage faults, that's actually wrong.
Let's think.
we can imagine a scenario like this. We have like 3 replicas. With 3 replicas, the replication quorum is 2. And like let's think the worst case. So there is like one prepare which is, say, replicated to A and replicated to B and is thus committed, but it is not replicated to C. And let's say A decides to evict this prepare because, well, this prepare is in A's checkpoint. And then a storage fault occurs. Again, with replication quorum of 2, actually a single storage fault should not make data available because, well, we should tolerate one storage fault.
Yeah.
But in this case, it actually might.
So okay, three replicas. One of them doesn't have the prepare at all. 2 of them have a prepare, but the prepare is only in one of those replicas checkpoint. Is it okay? The other question there is, are checkpoints also coordinated across replicas? So can we say that if replica 1 has applied a certain number of things to its LSM, then 2 has also applied them?
Precisely.
That is
precisely. This is a problem because we cannot actually say this. And we might end up in a situation where, like, okay, A decides to override this prepare because this prepare is in A's checkpoint.
In its checkpoint.
But B hasn't reached this checkpoint yet. So we have a situation where this prepare is logically replicated on 2 replicas. So it is on A's checkpoint, and it is in B's write-ahead log. So kind of like this like sounds legit because, well, we kind of like have replication quorum of 2. We promise that everything that is committed has durability of at least 2. And, well, like this prepare is on 2 replicas, like two replicas are aware of it. One through the checkpoint, another through a write-ahead log. But the problem here is that although logically we have this replication, physically we don't have this replication because the prepare as a prepare in write-ahead log exists only on a single replica, only on B, because A evicted it. And similarly, like this set of LSM tables, which stores this prepare in a checkpoint, also exists only on A. And this compromises durability. Because if you have, in this point, if you have fault in the prepare for write-ahead log in replica B, then you cannot actually, then you won't be able to actually repair that prepare, which is, okay, maybe this is fine because, well, there is a checkpoint on replica A, and rather than repairing from the log from B, you can repair from the checkpoint from A. But now, what happens if replica A gets a storage fault in a different area of a disk? So some kind of like uncorrelated storage faults. That would completely break the replication. So you have like 2 storage faults. They are at different areas. One is for write-ahead log. One is for LSM. Like normally we assume that we can actually repair uncorrelated faults. So kind of like a replica can, like we don't require one pristine data file. We only require that, hey, each block of a data file is available on at least 1 replicas, and then we like would like to be able to like piece together the actual data. But in this situation, that's actually not the case because you need 1 failure in a write-ahead log and 1 failure in a checkpoint to make both of them unavailable. So,
but in this case, the corruption on replica A is, which is at 2 different locations, is
no.
One is on replica B. Replica B's prepare is corrupted, and and so that prepare is essentially lost, and you can't recover that from any write ahead log. But what we are claiming is that's okay because at least one replica, which is replica A, has actually propagated that all the way to the LSM. But what if that block, which like the blocks that we need from replica A are also corrupted? Is that the issue?
Yeah. And moreover, like
Got it.
any block in replicas A LSM, if it is corrupted, it makes like it leads to a data loss, because I mean like
Mm.
you cannot like really say that, hey, this prepare is like in this particular LSM block, like, because LSM is like
Oh.
very like
Hmm.
complicated data structure, and like let's say
Yeah.
that on replica A we have corrupted some pointer near the root of the tree, which which means that, hey, actually we cannot use this checkpoint to prepare, because, well, like this data is gone. This data exists on a single replica in the cluster, and, well, normally we work around that, saying, okay, we cannot repair the checkpoint, but actually we can repair using write ahead log. But write ahead log repair also doesn't work
Don't
because we
have that.
have this prepare which is corrupted. So this is the issue here. While we preserve logical durability, while we say, hey, this data is logically present on a quorum of replicas, our physical durability is lost. This data is presented on a quorum of replicated replicas, but in a different form. So what we need to do is to ensure a handoff procedure, that you are only allowed to evict a prepare from your write ahead log if you know that this prepare is present on a quorum
On
of checkpoints.
checkpoints, yeah.
So you know,
Okay.
like your own checkpoint is not enough for that. You actually need to know that, hey, there is like this whole quorum of replicas which you have a checkpoint. So kind of like at some
Got it.
point you have a situation where this prepare is present in two checkpoints and in two write ahead logs. And this brings us to the actual bug in question. So we have this all prepare main function, which kind of like computes answers the opposite question. So right now we were thinking about, like, hey, if we get a new prepare, can we append it to our log? All prepare main is the opposite. It says, okay, this is the old prepare, which we at some point had in our log. Should we append it, or should we ignore it as too old? So basically, if we discover corruption in our log, should we try to repair it, or is it like old data which is going to be overwritten anyway? And this is like the exact
And this should like logically, this is a very it's a brain. I'm saying what is immediately what I'm immediately thinking. So this should technically be the uncheckpointed part of the log, right? So that should be the part that you should be allowed to repair.
Well, again, not necessarily, because we've established that op is checkpointed in your log is not sufficient condition
Not necessarily.
for safely evicting this.
Got it.
So again, you have to carry at least a checkpoint worth of stuff behind. And this is like, again, this is part of the command which I believe is correct. Availability condition. Each committed op must be present either in a quorum of write ahead logs or in a quorum of checkpoints. This is what we are trying to enforce. And this is, like, the actual bug, like this, like single paragraph, single logical inference, which of course was written by me and which is just flatly wrong. So or maybe actually, I think actually it like it used to be true before. I think it's even worse. So this thing is true if we don't do that checkpoint pipeline thing, where we say, hey, a replica is allowed to prepare a pipeline of prepares on top of checkpoint. And I think I was writing this code before we had checkpoint pipelining, but I landed the code after the pipelining landed, and kind of like the two together actually contradict each other. So anyway,
Got it.
the comment says if we commit the trigger +1, then we get an indirect evidence that the checkpoint is durably present on a quorum of replicas, and we then can proceed. Which was true while we didn't allow to prepare anything past trigger +1 past checkpoint trigger. But now we can prepare the whole pipeline of stuff on top of it. So in terms of our picture, so this is checkpoint trigger. This is checkpoint trigger. This is checkpoint trigger +1. And we actually can prepare all the way up to here. Like this whole orange thing we can prepare. So we can only can prepare stuff here. So if you actually, and this one, as a reminder, is prepare max. So kind of like, like trivial fix is to say that this is not op trigger, but op prepare max +1. And that, I think, would make this code correct, but that's the tricky thing, because
Alexei, I think when we came back to this this naive image, which is detached from the bug and detached from all of our discussion, I think lost our point a little bit. I still I think I got confused about that again. Why can we not say at op number trigger +1 that the checkpoint is durable? We can say on op trigger +1 that the checkpoint is durable on if I am a replica, it's durable on me, but it may not be durable on an entire quorum. That's the problem, right?
Okay, I'm kind of like confused a little bit what you are asking about. So are you asking about why this trigger +1 is wrong, or are you asking about what we discussed before, why we even need to why we even need this availability condition,
Yeah.
why we need to ensure that
I guess I do understand why we need the quorum. That is clear to me. But in this statement, the comment that we are saying is wrong. Can you scroll towards the right a little bit? The corresponding checkpoint. Can we really say that that when op trigger +1 is committed, the corresponding checkpoint is durably present on a quorum of replicas? We can't say. Can we ever say that? Is my question. Because
yes.
are we ever coordinating? Oh, we can say that. That's the part I'm confused about.
Yeah, because like all replicas execute the same code, and all replicas have the same prepare max. So like okay, let's like run some numbers here. Let's say that like our checkpoint interval is 32, our compaction interval is 8, and our pipeline is also 8. Then okay, and let's say that like I don't know, op 64 is a checkpoint, then 64 + 8, which is 72, it's trigger, and then 8 more, which is 80. It is it's prepare max. So every replica which is on checkpoint 64 can prepare up to and including 80. Now let's
Got it.
suppose let's suppose that you see orb equals 81, and this orb is committed. So like you get a ping from primary, and primary says, hey, my commit min, which is commit max for the cluster, is 81. What can you infer from this? So obviously, like if primary committed op 81, that means that the primary is on the next checkpoint.
Okay.
Okay, so I made an off by one checkpoint error. So if op 64 is a checkpoint, then kind of okay. So if we are in a neighborhood of op 80, we are about to transition to checkpoint 64. Значит, and that means that our actual checkpoint is actually
32 lesser. 32.
32. Yeah.
Okay. Got it.
So,
correct.
You get rumors from a primary that hey, primary has committed op 81. What can you infer about this? Well, first of all, you know that hey, primary obviously has this op 81, and if it is still on op 32, then it couldn't have appended op 81 to its log.
Yeah.
So the primary needs to be at this next checkpoint op 64. Moreover, you know that this op is committed. So you know that the primary has received quorum of prepare case. And that means that the quorum of replicas appended this checkpoint, appended this op 81.
So they're all on whoever sent a prepare OK are all on checkpoint 64. That is so we can ensure that.
Yes, because they also have the same prepare max. So
correct.
That's why we do this inference. So this for inference is correct. The bug here is that this shouldn't be a trigger. This should be op prepare max.
Prepare max.
Okay, and this creates a problem, which it might be a problem or it might be an opportunity. So what is the problem here? If you recall, we said that, hey, our journal should include at least a checkpoint interval, a compaction interval, and a pipeline. And we said that, hey, actually, we are going to take exactly that amount of slots. You actually can see this in the constants. So when we compute checkpoint interval, okay, yeah. So we have an assertion which says what is the allowed condition for checkpoint interval, and we say that hey, checkpoint interval plus compaction interval plus pipeline must fit in the write-ahead log. But then we actually derive checkpoint interval from this equation as maximum. We are saying okay, checkpoint is the largest checkpoint which can make this equation work, and this creates a problem because if we say that this is op prepare max plus 1, then we are actually running out of space in our write-ahead log because we get it up to, well, maybe I'm wrong here. So you'll drop will be to very carefully think about this. Well, maybe you actually could change this to prepare max plus 1. But I think I think that's actually not going to be the case. Well, yeah, because okay, so suppose we want op prepare max plus 1 here. But that means that when all replicas reach or prepare max, they cannot yet start editing old stuff because, well, they are waiting for or prepare max +1. And they cannot append or prepare max +1 because, well, that would evict the oldest prepare, which they think is still required. So you want this to see this or prepare max +1 to make sure that the checkpoint is committed, but no one actually has space in their log to append this prepare. So that's going to be a deadlock. I think one solution here is to like add like -1 here, which presumably would make it work. But actually, I also think that that's going to unnecessarily serialize the execution, because it seems like that critical prepare is basically a prepare which everyone waits to be committed so that they can like physically proceed to the next checkpoint. So it's kind of like mirrors this idea that, hey, let's do checkpoints asynchronously. So I think the fix here is slightly different. We could make replicas to directly track whose is on which checkpoint. So, and conveniently, this is handled by our pings. So if you...
Oh yeah, we send checkpoint IDs, right? That is what I remember.
Yes. We send checkpoint IDs and we send checkpoint ops. So as a replica, you could actually directly track which of your peers are on the current checkpoint. And if you understand that, hey, actually this checkpoint is committed, then you could go and stop preparing those old checkpoints, which I think is actually the right thing here. So we kind of like we don't wait for this or prepare +1 trigger. We like try to gossip information as fast as possible. So as soon as we have a quorum of checkpoints ready, then we can go and stop keeping all those old prepares in memory. Okay, so in terms of like how to implement this, I will need to look for this, but I think we actually used to have this code which tracked who is on which checkpoint. So that's like at least part of this fix is probably going to be reverting the commit which removed that infrastructure and adds it back. And then we'll need to change these or prepare max to kind of like take into account not only which checkpoint we are at, but also which checkpoints is everyone else at. And finally, one interesting thing here is that right now this or prepare max is durable, which means that if you crash and then you restart, then you start with the same or prepare max. For this new thing, I'm actually like not super sure. There might be like some tricky cases where like you execute normally, you collect a bunch of pings, you realize, okay, I can actually advance my prepare max because like those 5 other replicas are on a new checkpoint, so you append some new checkpoint, and then you crash, and then you restart. And after the restart, you of course don't have this information about other replicas, so you kind of have to conservatively assume that they are on the old checkpoint. But then at the same time, in your log, you have this new prepare. So you are okay. So if I appended this prepare before I crashed, that means that actually like at that point, I knew that there is a bunch of folks on the checkpoint, so I might as well extend my prepare max as well. But again, I don't know which dragons might be there. Okay.
So
Yeah.
basically, the op prepare max, which on each replica right now is a function of only that replica's checkpoint ID, is now becoming a function of a quorum. We can only, it has to be a function of, it has to take into account other replicas' checkpoint IDs as well. No.
Yes. And I think it's actually like probably like if you don't see so again, I think it might be useful to think about like the case of partial connectivity. So let's say that you can talk to primary and only the primary, which obviously means that you aren't going to collect a quorum of replicas because, well, yeah, like you only talk to a primary. But the primary actually can collect a quorum of replicas, and the primary can advance past this or prepare max.
Prepare
So
max.
this also should have a case where, like you receive a ping from a primary, and that ping says, "Hey, commit max is so and so." So you realize that, hey, actually, while I'm not hearing from those other folks, I know that commit max is past my or prepare max, which is determined simply by my checkpoint, so I can also advance my or prepare
Advanced.
max.
Got it.
This is actually like
Interesting.
touches some like larger refactor which we want to do at some point for partial connectivity. Is that like right now a lot of things in TigerBeetle are like sort of like RPC based, as that kind of like each replica, like replica A asks replica B answers replica A, and kind of like each replica kind of tries to form its own view of the world, but it looks, in case of partial connectivity, a little bit like that tale where three blinded philosophers try to describe an elephant, and one touches the elephant leg and says, "Hey, kind of like this is like very big," and the other like touches like elephant's trunk and says, "Hey, actually it's not that big," and the other like touches the tail and, "Hey, this is kind of like fluffy or whatever." So our overall plan is that replicas should kind of like gossip the global picture of the cluster, so that if even if replicas are like indirectly connected, they still converge onto the same picture of what cluster is. So we probably want to attach this to ping and have some kind of like merge operator which like unites this information. But right now we don't have this, and probably right now
Yeah.
it makes sense to solve this in a more ad hoc way. Okay, now I guess another question, like how do we know about this issue? This issue was found by Vopar. It was found on that my like super long branch, which is very bad about new sync protocol. So we don't have seed which reproduces it on the main branch, and I'm not sure that it would make sense to, well, maybe it would make sense to write replica test here. Although actually, yeah, it might be interesting. Yeah, it might be interesting to write a replica test which kind of like checks that it doesn't matter at which point you corrupt the LSM tree or like the write ahead log. You should always be able to like reconstruct the entire state.
Yeah.
Okay, I think that's like roughly all I had to share, and yeah, like that's your first real task, because I kind of hope that this shouldn't be like a complete rabbit hole of a fix, because like at least like crystal clear what is a bug, because yeah, like this is like this is just wrong, and it's like so great when you like can point to
Yeah.
like a very specific comment, even not even like the line of code, and say, hey, like Marklar's stupid here. So that's it.
Okay. Yeah, I think I understand the issue.
Okay,
It's
perfect.
time to understand it more deeply. Yeah.
So I guess then we can wrap up. Thanks for everyone who managed to watch it live despite this not having any kind of announcement. And as a reminder, this Thursday at 5 p.m. UTC, we'll have usual episode of, well, we have a slightly unusual episode of Iron Middle where we'll cover like non-technical stuff, where we'll cover engineering values of TechBill. Thanks for watching, and goodbye. And of course, thanks for Shitania for joining and helping to get this message about our structure of Write Ahead Log out there. Okay, bye.
Awesome. Thanks, Alexi. Bye.